Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today we will discuss about compressed domain processing. So in compressed domain, let us try to understand what is meant by this compressed domain. Now, as you know that in an image compression, images are represented in an alternative form. When I discussed about image transforms, we have mentioned that. So, when images are represented in that compressed form, that form we can consider that is the compressed domain. And for processing an image, you need to decompress the image so that you bring it to its original domain, for example, the spatial domain, perform processing. But can we do it directly in its representation in the compressed domain? So, this is the scenario when we have an image compression. That means you have an input object and there is a forward transform which transforms the image into a set of coefficients. We call them transform coefficients. Further, for efficient representation, which means requiring less storage and also less data size, we perform entropy encoding on those coefficients. That means there is certain kind of symbols. By exploiting the statistics of the symbols, we perform some encoding so that that is an efficient representation of it. So this is what a compression does. But then for decompression, you have to do the reverse operation, which means that your input is a compressed object, and then you perform first the entropy decoding, which will give you back once again these transform coefficients, because you have decoded those coding of the symbols, or which are the coefficients. Now, if you after decoding again you get back the transform coefficients, and then again you apply inverse transform to get the input object. Okay, so there is an error in this slide. So you should get an input object in this way. Now, when we say the processing of an image, when we consider if the image is available in the form of in its compressed format, then first you have to decompress it, and then you can process in the spatial domain using the algorithms what we have discussed so far. Mostly we have considered spatial domain representation of the image, like edge extraction or enhancement, whatever operations, thresholding. We discussed everything in spatial domain. But the fact is that these images, these processed images, again you need to store it in the compressed format. So you consider the practical scenario. Like if you see the mobile phones, when you capture an image, the image is stored in the compressed format because you have the limitations on storage. So you can store many images if it is compressed and then stored. Like the JPEG compression standard we have. So JPEG compression standard that we have to say is there, and mostly you will find those images are stored in this JPEG compression standard. And after doing some operations, even any applications in mobile phone also, then you have observed once again that your output is also again converted into that compressed format, because storing the processed image also needs to be efficiently done because of those limitations of memory. and those things. So mostly in most applications, your input is an image in compressed format. Also, your output is an image in the compressed format. So in between, you are performing your processing. Since your algorithms are mostly designed for spatial domain operations, so you require decompression for that, and for storing once again you require compression. So the question here is that, can we avoid these steps and do directly in the compressed domain? But there is still something no, you have to understand that the compressed image what you get, there are two steps of compressions I mentioned. That one is forward transform of the image to the transform domain, and then you perform entropy encoding. So when you are decoding, when you are decompressing, you perform entropy decoding, then only you get the transform coefficients. Now this coefficient space is called compressed domain. For example, you apply discrete cosine transforms, discrete cosine transforms. So this discrete cosine transforms coefficients, they form the space of compressed domain. So the space of coefficients of discrete cosine transforms is your compressed domain representation of the compressed domain. So can we just operate with this coefficient? So if I process using these coefficients and your output is also the transform coefficients of that image, that means processed image. So this operation practically we are calling as compressed domain operation, but still for efficient storage you require here entropy encoding of this symbol, and then you get output compressed image. So these steps, entropy decoding and entropy encoding, still remains in the compressed domain operations. Only saving what you are doing here, you are avoiding forward transform. So in this case it is inverse transform. You are applying inverse transform to get inverse transform to get the transform coefficients into spatial domain if you are doing it that, and then forward transform to get the transform. So you are avoiding them by directly operating in the transform domain. So that is a saving you can have when you are working with the computations directly in the compressed domain. So let me give you a very brief outline of JPEG compression scheme, because mostly that is what we will be considering in our subsequent discussions. We will be considering only images, and JPEG compression, it uses type 2 discrete cosine transforms. So what it does, you see that given an image, it partitions the image into non-overlapping 8x8 blocks. So these are all non-overlapping 8x8 blocks. Now each block is almost independently handled for compression. I said almost because I will explain that. So the first operation of that block is you perform level shifting, the DC shift, bring the DC part to 0, and then you apply discrete cosine transforms. You apply discrete cosine transforms, and then you do quantization of the coefficient. So if you have 8x8 block, you will have 8x8 coefficients. So because there are 64, if we say it's a 64 length, if I linearize it. So in the discrete cosine transform also, you know that from an n cross n image you get n cross n coefficients, type 2. So if I apply that transformation, so for example, this image is, let it be considered as say this block X, and you know that discrete cosine transformation matrix C8, what we have earlier discussed. So simply multiply C8X, and that will give you the density of that block. So the size will remain same. Now out of that 8x8 block, the first element of that array, which is 0th location, say if I represent in this way. So the first element, which is a 0, that means 0th row and 0th column. So the coefficients when the frequency component is 0, which is actually the DC component, as you know, for the transform, because the frequencies are 0. So this DC component has certain interpretations. It is actually the average of the intensity values of these 8 blocks. Now, I said almost because these DC components are separately encoded. These DC components are separately encoded, and all other AC components, so DC components of each block, they are separately encoded. So, you consider the sequence of DC components or arrangement of DC components, and then you encode them. So that is why there is certain kind of interdependencies in the encoded stream of the blocks, but all AC components, they are independently encoded. See, all other 63 coefficients. Now, how they are encoded? Now, for every coefficient, there is a quantization threshold, and this level of the quantization that is determined by using certain analysis on our psycho-visual analysis, that how those density components are affecting our perceptions, how much they are contributing to our perception, and so how much we are sensitive to those coefficients in our perceptions. So, more sensitive to that part, to our if it is more sensitive to our perception, we require fine quantization thresholds, means the quantization threshold value should be less. But for higher lower sensitive values, it could be very high. Usually low frequencies are more sensitive and high frequencies are less sensitive. So, we put lower thresholds there. So, you can see that quantization mask. DCT is type 2 event. So, this is the quantization mask, and you can see that these values are very high at the high frequency zone. So, these are the high frequency ranges, whereas the low frequencies part components, this is because you see the row number and column number, they are denoting the respective frequency components, normalized frequency components. So, lower the value, lower is the frequencies. So, this half you can see that these values are quite small. Now, there is a model, standard model. There is the international body of the standard who has suggested such quantization masks. There could be a few such quantization masks. I have just considered one of the most representative ones which are widely used. Now, after quantizing, what you get, you will find actually that many of the coefficients are set to 0. So, you will get this density coefficient array, it will be quite sparse. So, if I just show a little, in a typical example of 4 cross 4. So, you may get lot of zeros in this high frequency part, and there would be some non-zero coefficient, say because of the quantization, some non-zero value would be there, and when you are quantizing, there are all integers, as you understand that after quantization it becomes you are quantizing to integer values. So, there would be runs of zeros and there are non-zero values. So, there is a particular kind of scanning. So, what you do this, so after quantization your array would look like this. It is not 0, 1, there could be some other value, say 3, 6, but there would be some zeros, many zeros in this array elements. So, this we encode first by serializing this array elements into a sequence. So, there is a particular order. So, we call it zigzag order. So, this kind of order is followed like from here. So, you see that I will consider this one. Again, I will come here and then I will take this one. So, in this way it will proceed. So, in this way this order is proceed. Actually, the logic here is that I will be considering the lower frequencies ahead of any higher frequency term, because I want to see most of the zeros occur at the end of the sequence. So, most of the non-zero elements would be then in the beginning of those sequence. So, we convert it and then we do some kind of run length encoding. That means a run sub 0 and then the non-zero value. So, there is a non-zero value and then run sub 0. So, together there is a encoding. There is an Huffman encoding scheme. I am not going into details, but this is the entropy encoding part. So, the whole compression, this part, if I say this part is what is this entropy encoding task, but this transformation. So, finally, we will be considering for the compressed domain analysis to take this DCT coefficient. So, once I decode into this array, I have to apply the reverse the operations of I have to multiply the coefficients with the quantization mask, then I will get the respective DCT coefficients, and then perform all these operations, and then you get the respective image itself. So, our objective is to work with this DCT domain applying, and then after processing again I have to perform all these operations to compress the image for the processed output. So, as I was mentioning, in the compressed domain you simply perform the you simply avoid the overhead of forward and inverse transform. There is another thing also that you should know about JPEG compressions. So, what happens to the color images? So, I just mentioned of a particular image, so which means a particular channel, as a particular channel of color image. So, if it is a black and white or gray level image, it is the same, the algorithm which runs. But color images, what we do, instead of compressing each component independently, because there is high correlation of components, so we encode into its YCBCR space, because in CBCR you can work with less number of low resolution arrays. So, even that would also give good quality of images. But Y is the luminance part, which is taken with the same resolution of the array. So, that is compressed like the gray level image compressions what we discussed earlier. But for CBCR component, what we usually consider, suppose there are 4 8x8 blocks. So, these 4 8x8 blocks will be we call it basically macro block. So, first we transform this 4 8x8 block, that means 16x16 block, into YCBCR format, and then from there we consider for the Y component we partition them again into 4 8x8 block. For CBCR component, what we do that for complementary blue or CB component, only one block. So, that means from 16x16 block I will downsample it to an 8x8 block, and that I will compress for CB. Similarly, for CR also, from that 16x16 I will downsample it with 8x8. So, which means that given any RGB colored image, I will take a 16x16 block, again that non-overlapping blocks. I will perform the color transformations to get Y, CB and CR, each of 16x16 block of size. Then from there, Y component will be in the same resolution. So, there will be 4 8x8 block from the 16x16 blocks partitioning. From 16x16 block I will get 8x8 block, and so this is downsampled, and those are once again compressed in the same manner the way a particular gray level image is or a particular component is compressed. After that the algorithm remains the same. So, this is the only difference when you have the colored images. So, while applying this discrete cosine transform, we will be using two-dimensional discrete cosine transform, and we all know that there are type 2 DCT transforms, but I have also shown type 1 because it has its relevance in compressed domain processing. So this we have already discussed. So I just have shown the expression once again. So these are type 1 and type 2 DCT transformations, and they can be expressed in the form of matrix operations, transformation matrix operations that we have discussed. So in the matrix representations, I've just shown the type 2 DCT transformations. So you note that this is how the two-dimensional array is transformed. So it is basically post and pre and post multiplications of the transformation matrix of respective dimensions. So if it is m cross n array, so you have the type 2 DCT of order m or m point type 2 DCT matrix, transformation matrix, and this is n point type 2 DCT transformation matrix, and this is the way you are applying it. So what are the motivations for doing the compressed domain operations? You can compute with reduced storage, or you can also, as I mentioned, you can avoid overhead of okay, so this is not entropy decoding and encoding. As I say, entropy decoding and encoding will be there. So you avoid overhead of forward transform and inverse transform. Or if I consider the sequence, first inverse transform and then the forward, because you do the entropy decoding, get the alternative representations, that transform coefficients, then you perform inverse transform to get the spatial domain, perform spatial domain operations, then you perform the forward transform again to get the transform domain coefficients, and followed by entropy encoding. So that is what you do for spatial domain processing. Now in compressed domain processing, you do not require to perform forward transform or inverse transform and forward transform in that sequence. And also you can exploit spectral factorization for improving the quality of result and speed of computation. So this is another advantage if I use the transform domain representation, that spectral factorization. So because you have a structure, you have revealed the signal, or the image has revealed a kind of a structure. So from there, certain components selectively you can operate with certain components, say filtering basically. So you know the frequency band, so selectively you can enhance certain part and you can suppress certain part. So those kind of operations are possible in the transform domain, which was not possible in the spatial domain. So that is the advantage you have if you do compressed domain processing. Typical applications that we are going to discuss in the compressed domain. One is resizing, which means that you have an image of certain size, say some size, suppose say 100 cross 100, and then you are doing the some kind of resize it into say some 300 cross say 600. So arbitrary you can do. You can also, so this is a kind of upsampling operation. Similarly, you can perform the downsampling operation where you can reduce the dimensions of its width and height. Say from 100 square 100, you may do it say 50 cross 50. So this is the resizing operations. Filtering, we know already that if you have an image and a filter is basically it's a convolution operations. What you do, the filter has an impulse response, you perform convolution. Similarly, in the transform domain, if we understand from Fourier transform that you selectively allow certain frequency bands to pass and then reconstruct the image from there. Now, in the compressed domain, we are using block DCT transformations. So we call it block DCT because it is a discrete cosine transform of certain size of block, which is 8 cross 8 block. Sometimes it could be 16 cross 16 block also, that is for video compressions, but we are not going to discuss that here. So we would be mostly considering 8 cross 8 block DCT transformation. But if you have input in that form, so it would be interesting to see that how this kind of filtering operations could be performed directly there also. And enhancement we have also discussed, that which means that you are enhancing the mostly the contrast of the image, and can you do it directly in the compressed domain. So that was the kind of problem statement. So when we do the image resizing, so let us discuss some of these algorithms. So one of the things that I'm going to discuss here, which is called image halving operation. So it's a downsample operation. So you see that I have just represented it, since it is a compressed domain representation, and you consider all of them as blocks of DCT coefficients, and each one will be of 8 cross 8 block. So we suppose we have these 4 such adjacent blocks in that same array, in that array, and non-overlapping block. That is how the JPEG compression standard works in that fashion. So objective is that all these 4 blocks, can you convert it into a downsample form of a single block, which means I have a 16 cross 16 size of image, area of the image, which has been encoded, which has been represented by 4 8 cross 8 block DCT. Now, if I perform downsampling of this 16 cross 16 image to an 8 cross 8 size, and if I perform the DCT of that 8 cross 8 block of that image from the spatial domain, now whatever DCT coefficients we get, so this operation should also give similar DCT coefficients. It may not be exactly the same, but approximately the similar. So that now if I perform inverse DCT, you will get almost similar images of 8 cross 8 size. That is the downsampled version. So this operation, this downsampling, is a special name here. We call it image halving because both the dimensions along the width and height, they are getting reduced by a factor of half. So total area is reduced by 1/4, if you have noticed it. So if I consider the general scenario, say you have a larger image and there are all 8 cross 8 block partitioning of the image in the block DCT. So there what you do, that you take each 4 blocks and you convert it into a single block. So from this you get a block. Again, from this 4 block you get another block. From this 4 block you get another block, and this 4 block you get another block. So in this way you are actually having the whole image, and still you are retaining its compressed domain representation, because all are 8 cross 8 block DCT coefficients. So let us see how these operations can be done directly in the compressed domain. So let us try to understand that what is this kind of operations in spatial domain? A very simple operations. So here let me show you in the form of a linear transformation operations of this downsampling in the form of a matrix multiplication. Say this is a matrix of size 4 cross 5. Now you notice that this size is 4 cross 5. Suppose I have a vector, column vector, say this is x0, x1 to x7, and if I multiply this vector with this matrix D4 cross 8 matrix. So what you expect? So the first row will be basically it is the dot product of first row with this vector. So which means the first element would be x0 x1 plus x1 by 2. So this is the first row. Similarly, for the second row you have x2 plus x3 by 2, because you see that this is the positions, x2 everywhere it is 0. For the third element it is x4 plus x5 by 2, and the fourth element it is x6 plus x7 by 2, which means you are downsampling a column vector of size 8 of length 8 to a column vector of length 4 cross 1. So this is what you are doing. And if I consider a block of this of 8 cross 8 block, so I will have 8 such column vectors. I will have 8 such column vector, and if I multiply with this 4 cross 8, that will give me the output will be each column vector will be transformed into a column vector of 4. So I will get this. So now, which means I have already reduced the columns of this matrix, but there will be 8 such columns because each column is reduced. So there are 8 columns, so I will reduce that. So next what I will do, I have to reduce also the rows. So in the same form, I will get a transpose of this matrix. So if I get a transpose of this matrix, now you understand that there you get actually since each one is of 4 rows, so you will get 4 columns after transpose, and each is of vector, once again each is of vector of length 8. So once again you multiply with the same transformation matrix 4 cross 8 of this transpose one, you multiply with 4 cross 8. So what you get here? You get once again the column vector. Now you get, since there are 4, you get 4 column vectors of size 4. Since it is a transpose operation, once again you have to transpose this result to get the reduced size. So from 8 cross 8 block, finally you are getting 4 cross 4 block. So this is what a spatial domain operation is doing, and we can write it, these operations, say in the algebraic form. If I say I am considering x 0 0, so I can write it as x 0 0. Then I will be first I am doing this operation d 4 cross 8 into x 0 0, which will give me this value. Then I have to transpose it. So I will transpose this operation. Then I will multiply with d 4 cross 8. So I will get this vector. Once again I have to transpose it. So this is what we are doing. These operations, this matrix you get. So that would effectively give me a spatial domain data. So this you see that this is the spatial domain operations. I am taking average of consecutive pixels. It is not coefficients. These are all spatial domain representations. But in the spatial domain, I have from 8 cross 8 block to this. So this could be written as, so let me write, because it is spatial domain, let me write in the small form x 0 0. Not this is the transform domain representation, a spatial domain we should consider. So this can be simplified, this expression, if I write in this way. So as you know that this would be d4 cross 8 x 0 0, and this would be d4 cross 8 transpose. So finally this is the operation that would give me a 4 cross 4 block. So I can do these operations for this one also, this operation for this one also, and this one operation for this one also, which means from each one I will get 4 cross 4 blocks. The problem is that how I am going to arrange them in a 8 cross 8 form. So these are I am getting separately, but I have to place it in an array. So this quadrant should be filled by this one, this quadrant should be filled by this one, this quadrant should be filled by this quadrant should be filled by this one, and similarly. So as we have considered. So that is one of the reason that what we do, instead of using a column vector of 4 cross 8, if I use D4 cross 8 and then all zeros, so we write it 0 4 cross 4, 0 4 cross 8, which means all my rows, subsequent rows, they are all zeros. If I do it, now this will be augmented by 0 0 0. So now you can see that if I use this matrix for x 0 0, what I will get? I will get 8 cross 8 matrix, 8 cross 8 block, but only this quadrant will be the downsampled form and rest of them will be 0. For x 0 1, I have to do in a bit different way. So what I will do there, I will use rather the other one. That means my 0 would be here, and now it depends. For row operation, I will be using this one. For column operations, for row operations, I will be using this one. So it is not the same thing. For x 0 0, I am using this one. For x 0 1, for row operations, I will be using this one. So that would give me, these are all zeros, but it will place the 4 cross 4 blocks here. So in this way, I can play with these two, and finally I can add them. If I add these two, then in the resultant matrix, these zeros will be replaced by, so in the resultant matrix, if I add them, so now you have these two blocks and these are two zeros. And now you consider for subsequently for all other blocks also. So this is the system by which we do these operations. So let me then show these operations more mathematically, as I have explained in the following the same logic. As I mentioned that I will use this to downsampling transformation matrix by augmenting with 0 blocks, because I have to maintain the size as 8 cross 8. For each operations, I will get an 8 cross 8 block. So from 8 cross 8 block, I am getting also 8 cross 8 block operations in the spatial domain, but one of the quadrant is filled with the downsampled version of 4 cross 4 block, and that should be consistent with the arrangement what is shown in my theorem in the image itself. So these are the two unit I will be using judiciously. So this is the expression that is required. I mean, this is effectively expressing the thing computations what I have mentioned here. So if you note it carefully, then you can see that for the 0 0th positions, I have used the same matrix, this matrix only, P0 and P0 transpose, which I mentioned. For 0 1 position, it is P0 and P1 transpose, and for every other like this. Now, once again, you should note that this result in the spatial domain, this x00 is not this one, right? This is the spatial domain x00. It is the spatial domain operations. So what we want to do, because we want to do everything in DCT domain, and as the DCT is a linear and distributive operation. So let me once again explain why it is so. Suppose Pi, Xij and Pj transpose. Say these are the matrix multiplications which gives me the corresponding output in the processed domain. So in the DCT, what I can, so if I apply the transform, DCT transform of that 8 cross 8 block, I have to do like this, C8 and C8 transpose. That is what will, and C8 transpose is equal to C8 inverse, because it is an orthonormal transform. So this I can write in this way, C8 Pi, C8 transpose, once again C8 Xij, C8 transpose, and C8 Pj transpose, C8 transpose. So effectively, this is what? This is DCT of Pi. This is DCT of Xij, and this is DCT of Pj transpose. So these operations, which was a special domain operation, these operations, its equivalent transform domain operations would be this. Since I have the dct of xij, if I have the dct of xij, I have this, say x00, suppose x00 I want to do, dct of xij is already given to you when I and j is 0. Pi is also known to you. So it is dct of p0. This matrix is known. You can take its coefficients, transform domain coefficients of this arrangement. Similarly, this is also known to you. P0 transpose, if you take the transpose, its dct is also known to you. So now you can simply perform these matrix multiplications. What you will get? You will get also the result of these operations. If I write y, it is say I am writing it as yij. So this is the result you get, dct of yij. So this operation, if it is yij, so you are still getting dct of yij. And since there are summation, what I do, I will simply take sum of this, because dct sum of if I have a variable x plus y, then dct of x plus dct of y will be, that linearity operation is also there. You should note that all are of same dimension. So dimensional matching has to be there, that consistency has to be there in you. So this is how this compressed domain algorithm could be designed. Without going into spatial domain, I can directly play with these coefficients by using dct of p0 and dct of p1 appropriately. So mathematically, so as I mentioned, it's in linear and distributive properties that we are using, and this is the discrete cosine transform operations where I can perform this. But one of the problem here is that though we can do matrix multiplications directly in dct domain, but you will find that the downsampling matrix, which looked so sparse because there are many zeros, only few non-zeros, but dct of those downsampling matrix, those are not very sparse. You can see that there are many non-zero element. Earlier in P0, you have only few zeros. So if you remember, P0 was given like this, say 0.5, 0.5 and then all zeros. Similarly, these are 0, 0, then 0.5, 0.5, all zeros, and there are only 4. So most of them are zeros and only say 2 to 4 to 8 non-zero elements. In this case, it is much more. So which means that your multiplication and addition, it is not going to be reduced, and in fact it can be shown it is almost the same. So that means same in the sense, if I perform the inverse transform, then you perform these operations, the spatial domain operations, and then perform the forward transform. Whatever multiplication, addition you require, if I do it directly in the compressed domain, you require almost same. So there is not much of gain, and this method I should say that is not very much useful, because it is also a little bit complex. So as I mentioned, it is not great. Some results I can show you just to give you the idea that actually it will produce exactly the same what you get if you use bilinear interpolation. We did that bilinear disseminations because we have used the coefficient 0.5, 0.5. So simply you have taken the average of those two. So if you get bilinear interpolations in this form, then you get, even from the dct also you get exactly the same output. There would be certain because of the coefficients are becoming real from it has been displayed using transform, forward and inverse transform. Some variation would be there, but theoretically there is no variation. So what should we do? Now there what we do, actually we don't go for that kind of technique. Rather, we use some properties of DCTs to relate the upsampled and downsampled representations directly in the DCT domain. Instead of considering equivalent spatial domain operations, very one-to-one operations in DCT domain, we see that how coefficients are related. So there is a theory which is called subband density theory. Now I will just give the results of that theory, the relationships, that is how it captures. So I will just explain that how this kind of relationship holds. Say you consider these downsampling operations. So it is explained, suppose you have the original resolutions of the image, say x, and what we are doing, we are taking 4 pixels out of it, and then we are performing the averaging operations. That is what it is doing. So 2m, 2n, these are 4 adjacent pixels. I have used the even index because after that, suppose this is 0th location. So next location would be would be basically 2m plus 2 and say 2n plus 2, 2n or 2m. So it increases using each index by 2. So that is how this indexing is made, considered. But this is the expression, and it shows that if I have eminent array, then the relationship. So in the spatial domain, if I consider any particular array location, say mn, now this value is related to these locations in the high resolution image, which is 2m, 2n, 2m plus 1, 2n, okay, and their average is stored here. So this is a downsampled version. So it is not only the spatial locations but also the expressions, how it is done. Now what happens in the density coefficients? Suppose I take the density coefficients of this array, which is a larger array of size n cross n, and this size, as you see, this is n by 2 cross n by 2. So how they are related? So subband density theory, it deals with that, and it provides the useful results, practical results on this. So one of the approximation we can use in this case, relating these coefficients of higher resolution image to the lower resolution. Here it is basically the resolution twice of the size factor is 2 in both dimension. That is the higher resolution. So there we have this relationship. So this is the original density coefficients of the high resolution image, and then in the lower resolution part, both the dimension is reduced by 2. Then this coefficient, if this coefficient is scaled by 2 and all other are padded with 0, then you can get it approximates the coefficients of the higher resolution array. The size would be increased. It's something like you are repeating the value. Say if I have a low resolution image or some image in this size, say some values are there 2, 3, 50, 4, 6, 7, 8, 9. So some values are there. Now for higher resolutions, what I can do, I will simply replicate each positions by 2, then these positions by 3. So my size will be doubled, but my values would be replicated. So this could be a spatial domain operations, but in frequency domain, the effectively in density domain, what it does, suppose we have a say 4 cross 4 block of density. So you have a 4 cross 4 block of a density, or let us say 3 cross 3 block of a density, and then if I use if I consider a 6 cross 6 block of density, then these density coefficients can be mapped to this block 3 cross 3 block of this 6 cross 6, and all other could be set 0. So this is that 0 part. But while mapping it, I have to scale these coefficients by 2. So that is a interesting part. So if I scale these coefficients 2, then the effect would be like this. the effect would be like this, because no, you can see that also, that these coefficients, if I consider the block, these coefficients are repeated. So this no, scaling is done in that way. So this is a theory it tells, and this is how the approximation works. So this approximation is useful. So this is one kind of operations in the DCT domain. We will see that while relating the lower resolution block to higher resolution block that we can use. There is another operation in DCT domain that would be also useful while designing this algorithm. That means you can merge the adjacent DCT blocks into a larger DCT block. Now, I will be explaining with respect to one-dimensional representation, that means column vectors. It means that suppose I have two adjacent blocks of say length 8, then these are the DCT coefficients, these are DCT coefficients. Now, this operation, merging operation, we call it composition, will give me a DCT block of length 16, which means this is 16-point DCT. So, I can get two 8-point DCTs blocks, and I will get one 16-point DCT blocks, which means the length will be the same. This is merging. The reverse operation, that means if I give you 16-point DCT block and you decompose it into two adjacent 8-point DCT block, that is the reverse operation. So this is this is called block composition. This operation called block composition when you are merging two blocks, or if I have m blocks of length n DCT, n point DCT, each of n point DCT, I am merging this into mn length blocks, that is merging. Or if I give you mn length blocks, you can decompose them into m n-point blocks, that is called decomposition. So how do you do it? Now we can show that this can be done equivalently in linear operations using the linear operations in transform domain itself, directly in the transform domain. So there, let us see that actually the solution lies with the composition of matrices, matrix operations directly with your transform domain coefficients. Let me explain this part. So what we are doing here, for example, I am merging 8-point DCT blocks, say two 8-point DCT blocks. So what I am doing here, first I will be taking the inverse transformation, which is C8 inverse or C8 transpose. C8 is the DCT type 2 DCT block 8 cross 8, and that would give me the spatial domain DCT block. So if I have X, I will get X. Let me represent the capital uppercase for the transform domain representation, lowercase for this. So this is say X1 block, I will get X1. Suppose this is X2, I will still apply C8 inverse and I will get X2. Okay. So now if I concatenate them, this is my 16. So just concatenation, simply concatenation of these two give me length 16 cross 1. That is what is your 16 length vector. So there you apply forward transformation using 16-point type 2 DCT block. So there what you will get the 16-point type 2 DCT of this merged block. So your input was this and this is your output. Now can you perform all these operations in the transform domain, right? So you see that you are doing it. So what I will be considering, let us consider a column where this position is x1 and this is x2. The way it is arranged in your block structure of the compressed domain representation. I am just considering for the vector. So, x1, x2 they are stacked in the column. Now, let me consider a matrix where diagonal elements are this inverse block. So, this is this matrix is represented by sub matrices. So, let me consider this is a matrix. So, dimension is 16 cross 16, this matrix, and this C8 inverse is 8 cross 8. This 0 is a 0 matrix of 8 cross 8 block. This is also 8 cross 8 block, and sub matrix, this is also this. So, using sub matrix algebra, it is as same as the matrix algebra. So, only the dimension matching you have to consider. So, what we do here, it is C8 inverse into x1 plus 0. That means you multiply this and add them. Similarly, 0 plus C8 inverse x2. That is your result of this matrix. Okay. So, what you get? The stacked result. So, this is equivalent to this concatenation. Then you perform forward transform C16. So, the whole thing I can write once again in this way. Say this is your matrix x1, x2, and then C8 inverse 0, 0, C8 inverse. And then you multiply with C16, that would give me the density of 16 point. So, if I multiply these two matrices, that would give me a transformation matrix, because matrix, these two can be composed, matrix multiplication is associative. So, if instead of multiplying in this way, I will directly multiply with this transformation matrix and I will get the block transformation. So, this matrix is called block composition matrix. So, I have given with respect to the 8-point density example. I will elaborate this computation further in my next lecture. So, today let me stop here. Thank you very much for your listening.